October 14th, 1941. Detroit Arsenal Tank Plant, Warren, Michigan. The arc flashed blue-white in the darkness of the welding bay, casting harsh shadows across the face of the man holding the electrode. James McNally, chief welding foreman, watched the molten metal pool and spread between two plates of homogeneous armor steel, each one 3 inches thick. The weld looked perfect. Smooth bead, proper penetration, no visible defects. Then it cracked. A sharp metallic ping echoed through the bay as a hairline fracture appeared in the cooling metal, spreading like lightning across the joint. McNally killed his arc and stepped back, pulling off his hood. The 5th failed weld of the morning. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Behind him stood Owen Skelton, Chrysler's production manager, and 3 Army Ordnance Department inspectors. They had been standing there for 2 hours, watching McNally attempt to join armor plates using the specifications that every military arsenal in America had followed since 1938, the specifications that no longer worked. Skelton broke the silence. "We're supposed to deliver the first M3 medium tank in 6 months. That tank requires approximately 8,000 welds. If we cannot join 2 plates without cracking, we will not build tanks. We will build expensive steel sculptures that split apart when somebody shoots at them." The senior inspector, Colonel Richard Hayes, cleared his throat. "The specifications are quite clear, Mr. Skelton. Armor plate shall be joined using mild steel electrodes with cellulose coating, following procedure AR7-38. These procedures have served American arsenals for 2 decades. McNally tossed his electrode holder onto the workbench. "With respect, Colonel, those procedures were developed for ship armor and fortifications. Nobody was trying to mass-produce tanks back then, and nobody was trying to weld high-carbon armor steel in an assembly line environment where we need 1 weld every 3 minutes for 18 hours a day. The fundamental problem facing American tank production in late 1941 was elegant in its simplicity and devastating in its implications. The armor steel that protected tanks from enemy fire was the same steel that could not be welded without cracking. The high carbon content that made armor hard enough to deflect shells also made it brittle enough to fracture during the welding process. Traditional welding procedures assumed unlimited time, optimal conditions, and master craftsmen who understood metal behavior through decades of experience. Chrysler's tank production plan assumed none of those things. The Detroit Arsenal was designed to build tanks like automobiles, using assembly line techniques with semi-skilled workers performing specific operations repeatedly. The vision required welding processes that were fast, reliable, and executable by workers with minimal training. Army Ordnance specifications were written for craftsmen who spent 4 years learning their trade. McNally needed processes that could be taught in 2 weeks. The collision between industrial necessity and military tradition was about to force a revolution in welding technology. That revolution would begin not in a laboratory or engineering office, but on the production floor, with a foreman who was willing to break every rule that stood between blueprints and finished tanks. 3 days after the cracking demonstration, McNally gathered his small team of welders in the corner of the fabrication shop. He had recruited 8 men, none of them from traditional arsenals. 2 had worked building pipelines across Oklahoma. 3 came from bridge construction in Pennsylvania. 1 had welded pressure vessels for chemical plants. The last 2 were automobile workers from Ford who had never welded armor plate in their lives. McNally laid out the problem with characteristic bluntness. "The Army says we use mild steel electrodes. Those electrodes create welds that crack on armor steel about 60% of the time under production conditions. We need welds that work 99% of the time, and we need them completed in 3 minutes or less. The Army specifications will not get us there. So we're going to develop specifications that will." Thomas Whitfield, one of the pipeline welders, raised his hand. "You're talking about ignoring military procedures. That seems like a quick way to get arrested." McNally shrugged. Mr. Skelton told me yesterday that Chrysler has a contract to deliver 1,000 tanks. He also told me that contract is worthless if we cannot weld armor without cracking. He gave me 60 days to solve the problem using whatever methods I consider necessary. After 60 days, either we have working procedures or Chrysler cancels the contract. I'd rather face court-martial than tell American soldiers they're going into combat in tanks that fall apart because we followed procedures that don't work. The experimentation began immediately. McNally's team set up a testing area in the furthest corner of the fabrication shop, away from official inspections and prying eyes. They requisitioned armor plate samples, various types of welding electrodes, and every technical manual they could find on armor metallurgy. Then they started trying things that Army regulations explicitly prohibited. The first breakthrough came from an unexpected source. Harold Chen, one of the former automobile workers, had never welded armor before joining Chrysler. His lack of experience became an advantage. While the experienced welders approached armor with caution and traditional technique, Chen treated it like thick automobile steel. On his third attempt, he picked up a nickel alloy electrode, originally designed for stainless steel fabrication. The Army. Manual says mild steel electrodes only, McNally warned him. Chen shrugged. The Army manual isn't working. Let's try something that might. The nickel electrode created a weld that looked different from traditional mild steel joints. The bead was brighter, almost silver in color. The heat-affected zone appeared narrower. McNally let the joint cool for 30 minutes, then subjected it to the same stress testing that had cracked every previous weld. The joint held. No visible cracks, no fractures, no defects. McNally stared at the intact weld for a long moment. Do that again. Same materials, same technique. I want to see if it's repeatable. Chen welded 3 more joints. All held. The nickel alloy electrode that violated Army specifications had just solved the cracking problem that threatened the entire tank program. But understanding why the nickel electrode worked required digging into metallurgy that most welders never studied. McNally brought in Arthur Morrison, Chrysler's senior metallurgist, to examine the successful welds. Morrison spent 2 days analyzing the joints, measuring their chemical composition and studying their crystal structure under magnification. His explanation, delivered to McNally and Skelton in a hastily called meeting, revealed the fundamental problem with traditional welding procedures. The armor steel contained approximately 0.5% carbon content. That carbon made the steel hard, but it also made it prone to forming brittle structures called martensites when heated and rapidly cooled. Mild steel electrodes added more carbon to the weld pool. The result was a joint even more prone to cracking than the base metal. Nickel electrodes created a fundamentally different metallurgical outcome. Morrison drew diagrams on a chalkboard, explaining how nickel atoms disrupted the formation of harmful crystal structures. The nickel also reduced the cooling rate of the weld, preventing the rapid temperature changes that created stress, concentrations. The addition of roughly 18% chromium and 8% nickel in the electrode produced austenitic welds that remained ductile even after cooling. Skelton listened to the technical explanation, then asked the only question that mattered. Can we use these nickel electrodes in production? Can we teach workers to use them reliably? And will the Army accept tanks built with procedures that violate their specifications? McNally answered the first 2 questions immediately. Yes and yes. The nickel electrodes are actually easier to use than mild steel. They create more stable arcs and require less skill to achieve good penetration. I can train workers to use them in less than a week. The third question hung in the air, unanswered. Using unauthorized welding procedures on military equipment was not a minor deviation. It was a direct violation of procurement regulations. If the welds failed in combat, people would die. If Army inspectors discovered the unauthorized procedures before production began, Chrysler would lose the contract. McNally was proposing to bet the entire tank program, and possibly the lives of American soldiers, on welding methods that no military authority had approved. Skelton made the decision that would define the program. We proceed with nickel electrodes. We document everything, we test extensively, and we build sample hulls that we subject to every stress test the Army can devise. When we're ready, we present them with completed tanks that work, rather than theoretical procedures that might work. Success will justify the methods. November brought additional discoveries that further deviated from Army specifications. Whitfield, the pipeline welder, noticed that welds completed early in the morning when the shop was cold had higher failure rates than welds completed in the afternoon after the building warmed up. The observation seemed trivial until Morrison explained the metallurgical implications. Armor steel's tendency to form brittle structures increased dramatically when welded at temperatures below 60 degrees Fahrenheit. Preheating the steel before welding reduced thermal shock and prevented cracking. Army procedures specified no preheating. Preheating required additional equipment, additional time, and additional training. It complicated the production process, but it also worked. McNally added preheating stations to his production plan, stations where armor plates would sit under radiant heaters for 15 minutes before welding, bringing the metal to approximately 150 degrees. The experimentation continued through November and into December. Chen discovered that maintaining electrode storage in heated cabinets at 100 degrees prevented moisture absorption that caused hydrogen cracking. Whitfield developed backing strips that supported the weld pool and prevented burn-through on critical joints. Morrison created post-weld cooling procedures that prevented rapid temperature changes. Each innovation deviated further from Army specifications. Each innovation also improved weld quality and reliability. By December 7, 1941, when Japanese aircraft attacked Pearl Harbor and transformed American industrial mobilization from theoretical planning to desperate necessity, McNally's team had developed a complete welding procedure that bore almost no resemblance to official military standards. The first complete tank hull welded using the unauthorized procedures was assembled in January 1942. The hull required 3 days to complete, far slower than the eventual production pace, but fast enough to demonstrate feasibility. McNally personally inspected every weld, more than 800 individual joints. He found 2 minor defects, both easily repaired. The hull was then subjected to stress testing that would have destroyed a hull built to Army specifications. Engineers applied hydraulic pressure, simulating the weight of a 30-ton vehicle on rough terrain. They vibrated the hull at frequencies matching running gear resonance. They thermal cycled it between -40 and +120 degrees Fahrenheit. They even fired captured German 37mm armor-piercing rounds at the hull plates from 300 yards. The welds held. Every single joint remained intact. The nickel electrode procedures had created armor joints stronger than the armor plate itself. Colonel Hayes arrived at the Detroit Arsenal in late January for a routine inspection. He found the completed hull sitting in the testing area, battle-scarred from the abuse it had endured. McNally met him at the welding bay, carrying documentation that detailed every deviation from Army specifications. "Colonel, we need to discuss our welding procedures." McNally's directness surprised Hayes, who had expected the usual careful maneuvering around military inspectors. Hayes examined the documentation in silence. His face revealed nothing as he read through page after page of unauthorized techniques. Finally, he looked up at McNally. "These procedures violate Army Regulation 7-38 in approximately 14 distinct ways. You are aware that using unauthorized welding methods on military equipment is grounds for contract cancellation and possible criminal prosecution." McNally nodded. "Yes, sir. I am also aware that the tanks we're building with these procedures have weld joints that consistently test stronger than tanks built to your specifications. That hull you see in the testing area has been subjected to stress testing that would have fractured a regulation-built hull. It has 0 weld failures." Hayes walked to the test hull and examined the welds closely. The silver-colored bead patterns were immediately distinctive, clearly different from traditional mild steel joints. He ran his fingers along several seams, checking for cracks or defects. He found none. "Show me your welders in action." If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. McNally led Hayes to the welding stations where 3 workers were assembling a hull section. The workers wore standard protective equipment, but moved with the efficiency of automobile assembly line operators, rather than traditional arsenal craftsmen. One worker, a former secretary named Margaret Russo, who had learned welding 6 weeks earlier, was completing a vertical seam on a bulkhead plate. Hayes watched in silence as Russo struck her arc, maintained a steady bead progression, and completed the joint in less than 4 minutes. The weld looked professional, smooth, with consistent penetration. Hayes checked her electrode holder and examined the silver-coloured rod. "This is a nickel-chromium alloy electrode," he observed. "Not mild steel, not what the specifications require." "No, sir," McNally agreed. "It's also what allows Miss Russo, who had never seen a welding torch before December, to create joints that pass every quality test we can devise. Traditional electrodes require years of experience to master on armor steel. These allow us to train competent welders in 2 weeks." Hayes turned to Russo. "Young lady, how long have you been welding?" Russo pulled off her hood, revealing a young woman barely 20 years old. 6 weeks, sir. Mr. McNally's team taught me the basics in 3 days. I've been practicing on scrap steel ever since. This is my first actual hull component." Hayes examined the weld she had just completed. He pulled a magnifying glass from his pocket and studied the bead for defects. He found none. "And how many welds have you completed today?" Russo checked her tally sheet. "This is number 43, sir. My shift started at 6 this morning. The colonel did the mathematics immediately. 43 welds in approximately 8 hours meant 1 weld every 11 minutes, accounting for material handling and positioning time. That pace, multiplied across hundreds of workers, would enable the production volumes Chrysler had promised. Traditional arsenal, welders completing 3 or 4 welds per day would never achieve such output." Hayes spent the next 4 hours examining McNally's welding operation. He watched workers of all backgrounds, from former farmers to housewives to automobile mechanics, completing complex armor joints with efficiency that seemed impossible for their limited experience. He examined completed hulls, studied metallurgical test reports, and reviewed training documentation. Finally, he asked McNally to assemble everyone involved in developing the unauthorized procedures. 15 people gathered in the conference room. McNally, his welding team, Morrison, the metallurgist, Skelton, and several production supervisors. Hayes stood at the head of the table, the Army Regulation Manual open before him. "Gentlemen and ladies, what you have developed here represents the most comprehensive violation of military procurement procedures I have encountered in 20 years of service. You have substituted unauthorized materials, invented unauthorized techniques, and trained workers using unauthorized methods. By regulation, I should recommend immediate contract cancellation." The room fell silent. McNally's jaw tightened, but he said nothing. Skelton began to speak, but Hayes raised his hand. "However, I am also required to report on the feasibility of contracted production goals. After examining your methods, your workers, and most importantly your results, I must conclude that your unauthorized procedures are the only way this nation will produce tanks in the quantities the war requires. I will recommend to the Ordnance Department that your welding specifications become the new standard for all armor fabrication in the United States." The relief in the room was palpable, but Hayes was not finished. "I will also recommend that Mr. McNally be brought to Washington to train welding supervisors from every tank plant in America. What you have developed here is not simply a better welding technique. It is a complete reimagining of how armor can be joined in a production environment. That knowledge needs to spread immediately." By March 1942, McNally's nickel electrode procedures had been formalized into a new Army Technical Manual, TM 9-1731B. The manual represented a complete departure from traditional arsenal practice. It specified nickel-chromium alloy electrodes, with 18% chromium and 8% nickel content. It required preheating armor plates to 150 degrees Fahrenheit before welding. It mandated electrode storage in heated cabinets to prevent moisture absorption. It established post-weld cooling procedures that prevented thermal stress. Most revolutionary of all, it assumed welders could be trained in weeks rather than years. The manual included simplified instruction methods, practice exercises that developed specific skills, and quality control procedures that did not require expert judgment. It was designed for mass production, not craftsmanship. The contrast with German tank welding procedures was stark and would prove strategically significant. German tank plants employed highly skilled welders who had completed traditional 4-year apprenticeships. These craftsmen produced beautiful welds, smooth and aesthetically perfect, but they worked slowly, completing perhaps 20 to 30 linear feet of weld per day. German tank production relied on manual arc welding exclusively throughout the war. Individual welders were assigned to specific seams on Panther and Tiger hulls, ensuring consistency but limiting production speed. German armor steel presented even greater challenges than American plate. Metallurgical analysis of captured German tanks revealed carbon content ranging from 0.50 to 0.75%, significantly higher than American specifications of 0.30 to 0.40%. The high carbon content made German armor extremely hard, but also extremely prone to cracking during welding. German engineers compensated by using elaborate joint designs, including interlocking spike connections reinforced with steel dowels. These joints were mechanically strong but required extensive machine work and fitting time. The Germans never solved the fundamental metallurgical problem. Their welds frequently cracked under combat conditions. Allied intelligence reports documented numerous instances of German tank hulls splitting along weld seams after receiving hits that should have been survivable. A Panzer IV examined in Tunisia had a 6-foot crack running through the hull side weld, caused not by penetration but by the shock wave from a 75mm shell impact. The brittle welds could not absorb the energy. Soviet engineers took a different approach entirely. Under the leadership of Professor Yevgeny Oskarovich Payton, the Institute of Electric Welding developed automatic submerged arc welding for tank production. The Payton method used a continuous wire electrode fed automatically through a welding head, with the arc submerged under a protective flux. The technique was fast, requiring minimal operator skill, and produced excellent quality joints. Soviet 34 production, relocated to Nizhny Tagil after the German invasion, employed 19 automatic welding units that replaced 280 skilled welders with 57 semi-skilled operators. Productivity increased tenfold. But the Soviet approach required specialized equipment, dedicated power supplies, and fixed production positions. It worked brilliantly for the relatively simple 34 hull, but could not adapt easily to complex geometries or varied production requirements. The Patton method was automation, not flexibility. The American nickel electrode approach occupied a middle ground between German craftsmanship and Soviet automation. It retained the flexibility of manual welding while democratizing the skill requirements. A semi-skilled American welder using McNally's procedures could achieve quality matching a German master craftsman in a fraction of the time, without requiring the specialized equipment of Soviet automation. The strategic implications became apparent as production statistics accumulated through 1942 and 1943. The Detroit Arsenal, using nickel electrode welding, was producing Sherman tanks at rates exceeding 800 per month by late 1942. Each tank contained approximately 40 linear meters of armor welds, all completed in less than 150 man-hours of welding time. German tank production, relying on traditional methods, peaked at approximately 600 vehicles monthly across all models and all factories combined. The mathematics of industrial warfare were writing themselves in weld beads and production tallies. Germany's carefully crafted tanks, built by master welders using procedures refined over decades, were being overwhelmed by American tanks built by former secretaries and farmers who had learned to weld 6 weeks earlier. Quality was not irrelevant, but quantity multiplied by adequate quality defeated perfection multiplied by scarcity. McNally spent most of 1942 traveling between American tank plants, teaching his procedures to welding supervisors from Pennsylvania to California. At each facility, he encountered initial resistance from traditional welders who viewed nickel electrodes as inferior substitutes for proper mild steel. At each facility, he won converts by demonstrating results. A good weld that can be completed in 4 minutes by a worker with 2 weeks training beats a perfect weld that requires 30 minutes and 4 years of experience, he would tell skeptical foremen. We are not building jewelry, we are building weapons. Adequate and available defeats perfect and scarce. By early 1943, every American tank plant had adopted McNally's procedures. Pressed Steel Car Company in Pennsylvania, Pacific Car and Foundry in Washington, Fisher Tank Arsenal in Michigan, all used nickel-chromium electrodes, preheating stations, and moisture-controlled electrode storage. The standardization enabled worker mobility between facilities and allowed rapid production increases as demand surged. The procedures also proved adaptable beyond tanks. Shipyards building Liberty cargo vessels adopted nickel electrode welding for hull fabrication. Aircraft manufacturers used similar techniques for welding wing spars and fuselage frames. The revolution that began with a foreman trying to build tanks spread across American industrial production, transforming how high-strength steel could be joined under mass production conditions. Field performance validated the technical decisions in ways no laboratory test could predict. Sherman tanks landed on North African beaches in November 1942, carrying armor welds completed by workers who had learned their trade weeks earlier. The tanks were hit by German anti-tank guns, struck by Panzerfaust rockets, and subjected to combat stresses that exceeded every engineering specification. The first comprehensive field report came from repair depots in Tunisia in March 1943. Ordnance officers examined 67 damaged Shermans recovered from battlefields around Kasserine Pass and Spitler. 41 tanks had suffered armor penetrations from German 75mm and 88mm guns. 26 had been struck by anti-tank rounds that failed to penetrate but delivered tremendous kinetic energy to the hull. Engineers documented the damage patterns with photographs and metallurgical analysis. The findings astonished even McNally. Of the 67 damaged tanks, exactly 0 showed catastrophic weld failure. Several had welds adjacent to penetration points, where the armor plate itself had been punched through. The welds remained intact even when the surrounding metal had failed. One Sherman examined at the Casablanca depot had taken an 88mm hit directly on a hull side weld seam. The shell penetrated the armor and detonated inside the tank, killing 3 crew members. But the weld itself had not cracked or separated. The joint held even as the armor plate it joined was destroyed. Lieutenant Colonel Frank Harrison, chief of the North African Ordnance Technical Intelligence Team, wrote in his April 1943 report that the weld joints on American tanks are proving more durable than the armor they connect. We are observing failures of armor plate, but not failures of the welded connections. This suggests the welding procedures exceed the strength requirements by a comfortable margin. The pattern repeated in Sicily, Italy, and France. Repair depots examined thousands of battle-damaged Shermans. They documented armor penetrations, turret damage, suspension failures, and engine fires. Weld failures remained statistically insignificant. A Sherman knocked out near Monte Cassino had been hit 7 times by German anti-tank fire. The hull showed 4 penetrations and 3 partial penetrations. Every weld remained intact. The tank was repaired, re-welded where necessary using the same nickel electrode procedures, and returned to service within 11 days. The contrast with German experience became starkly apparent as Allied forces captured increasing numbers of disabled panzers. A Tiger tank recovered near Anzio in February 1944 showed 3 distinct weld cracks, none related to combat damage. Metallurgical examination revealed the cracks had originated during manufacturing and propagated slowly under operational stress. A Panther examined after the Falaise pocket collapse had a fractured hull glacis weld that investigators traced to thermal stress during production welding. The German armor was harder than American plate, achieving Brinell hardness numbers exceeding 300 compared to American values around 250. But hardness without ductility created brittleness that manifested in failed welds under battlefield conditions. Intelligence reports from repair depots in forward areas documented repair procedures that further validated McNally's methods. Field maintenance battalions welded damaged Sherman hulls using portable equipment and the same nickel-chromium electrodes specified for factory production. Tanks with penetrated sponsons, damaged turret rings, and fractured track mounts were repaired at forward positions and returned to combat. The repairs, completed by mechanics with minimal welding training under field conditions, proved as durable as factory joints. A Sherman repaired near Saint-Lô in July 1944 was hit again 3 weeks later. The new damage occurred 30 centimeters from the field repair weld. The repair weld held perfectly while adjacent armor failed. By war's end, in 1945, American plants had produced approximately 88,000 to 90,000 tanks using McNally's welding procedures. German production totaled approximately 24,000 tanks across all models. The 10-to-1 production advantage enabled American and Allied armored forces to attack with numerical superiority that German tactical skill could not overcome. At Normandy, in the Ardennes, across the Rhine, American tank units advanced, knowing that vehicle losses could be replaced within days. German panzer divisions fought knowing that each destroyed tank represented an irreplaceable asset. The human cost was measured in lives saved as well as enemy defeated. Sherman crews survived hits that would have killed them in tanks with inferior welds. The durability of American armor welds, dismissed by pre-war experts as inferior to German craftsmanship, proved superior in the environment that mattered most. Actual combat, McNally never sought recognition for his role. He spent the war years training welders, refining procedures, and solving production problems. By 1944, more than 200,000 American workers were using techniques he developed. Few knew his name, the welds they created daily, thousands upon thousands of joints joining armor plates into tanks, were his monument. The technical legacy extended far beyond World War II. The nickel electrode procedures McNally developed became foundational standards for high-strength steel fabrication worldwide. Modern armor welding, whether on main battle tanks or armored personnel carriers, uses evolved versions of the same basic approach: nickel-based filler metals, preheating protocols, moisture control, and simplified techniques accessible to semi-skilled workers. The procedures are now codified in international standards, taught in welding schools globally, and considered fundamental knowledge in the field. The democratization of welding skill that McNally pioneered had implications beyond military production. Post-war industrial expansion relied on rapidly trained workers executing complex fabrication tasks. The heavy construction boom of the 1950s and 1960s, building bridges, skyscrapers, and infrastructure, depended on welding techniques that could be taught quickly and executed reliably. McNally's insight that complicated processes could be simplified without sacrificing quality-enabled industrial scaling that traditional craft approaches could never achieve. The philosophical challenge McNally posed to military traditionalists in 1941 remained relevant decades later. Specifications existed to ensure quality, but specifications that prevented necessary production were worse than useless. Rules that assumed unlimited time and master craftsmen failed when confronted with industrial war requiring thousands of tanks monthly. The tension between perfectionism and pragmatism, between craft tradition and production necessity, was resolved not through compromise, but through innovation that rendered the old debate obsolete. Colonel Hayes, who risked his career approving unauthorized procedures in 1942, rose to brigadier general by war's end. In his retirement memoir published in 1962, he reflected on the Detroit Arsenal decision. McNally taught me that regulations serve victory, not the reverse. When procedures prevent success, change the procedures. The Army existed to win wars, not to enforce regulations that made winning impossible. McNally understood that before I did. Owen Skelton, Chrysler's production manager who authorized the experimentation, became vice president of the corporation after the war. In a 1958 interview with Fortune magazine, he was asked about the keys to successful military production. Skelton's answer was immediate: find people who solve problems rather than explain why problems cannot be solved. McNally looked at cracking welds and asked what we could change. Army inspectors looked at the same cracks and cited regulations. We won the war with McNally's attitude, not the inspectors. Arthur Morrison, the metallurgist who explained why nickel electrodes worked, went on to a distinguished academic career at MIT. His textbook on welding metallurgy, published in 1955, became standard reading in engineering programs worldwide. The chapter on armor fabrication included detailed analysis of the Detroit Arsenal innovations, explaining to future generations of engineers how fundamental understanding of material science enabled production breakthroughs. Margaret Rousseau, the former secretary who became a welder, worked at the Detroit Arsenal until production ended in 1945. She then joined Ford's aircraft engine division, applying her welding skills to jet engine fabrication. In a 1998 oral history interview conducted by the Smithsonian, she recalled her wartime experience with characteristic modesty. I was just doing my job, but it felt important, knowing that the tanks I helped build were protecting American soldiers. Mr. McNally made us believe that our work mattered. He was right. The welds themselves, those thousands of joints completed in frantic haste by inexperienced workers using unauthorized techniques, survived. Sherman tanks preserved in museums from Texas to Belgium still show the distinctive silver-colored bead patterns of nickel electrode welds. A Sherman hull recovered from a reef near Saipan, submerged for 80 years in corrosive seawater, revealed welds that remained intact and corrosion-free, while the surrounding steel had deteriorated severely. The nickel alloy that saved production time in 1942 ensured longevity no one anticipated. The final measure of McNally's achievement was written not in technical reports but in absence. American tank production never encountered a welding crisis. There were no desperate telegrams reporting cracked hulls failing inspection. There were no production delays traced to weld defects. There were no combat losses attributed to failed armor joints. The thing that every expert predicted would be impossible, reliable high-speed welding of armor steel by semi-skilled workers, simply worked. It worked from the first production hulls in early 1942 until the last tanks rolled off assembly lines in 1945. The story that began with James McNally watching cracks appear in test welds ended with American industrial dominance built on millions of successful joints. The foreman who chose to ignore regulations and pursue results enabled a production revolution that traditional military thinking said could not happen. His unauthorized nickel electrodes, preheating stations, and simplified training methods did not merely improve welding, they transformed it from a craft requiring years to master into a process accessible to anyone willing to learn. The transformation reached backward to redefine what quality meant in industrial warfare. Quality was not the perfection of German master craftsmen producing beautiful welds on 20 tanks monthly. Quality was the adequacy of American semi-skilled workers producing functional welds on 800 tanks monthly. Quality was joints strong enough to protect soldiers and simple enough to be replicated by thousands of workers across dozens of factories. October 14th, 1941, McNally watched welds crack and faced industrial catastrophe. December 19th, 1945, the last Sherman tank completed at Detroit Arsenal carried armor welds fundamentally identical to the unauthorized joints McNally's team developed 4 years earlier. Between those dates, approximately 22,000 tanks were built at that single facility. Across all American plants, 88,000 to 90,000 tanks were produced using techniques that began as experiments in a corner welding bay, hidden from official inspection and executed in defiance of military regulations. The revolution happened because one foreman asked the right question. Not how do we follow regulations, but how do we build tanks? Not what are the approved procedures, but what actually works. Not what have we always done, but what must we do now. McNally's answer, delivered in crackling arcs and molten metal pools across millions of weld beads, won industrial battles before the first Sherman fired a shot in anger. The illegal arc method that McNally pioneered was never truly illegal. It was unauthorized, untested, and unprecedented. It violated every regulation that stood between American industrial capacity and the weapons democracy needed to survive. In violating those regulations, McNally and his team created standards that would guide armor fabrication for the next 8 decades and counting. The welds that military experts said could not be made by inexperienced workers using unapproved materials became the welds that built the arsenal of democracy. Sometimes the strongest joints come not from following rules, but from knowing which rules must be broken so that other, more important things do not break first. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.